Okay, so I have apparently been classified as something resembling a geologist, but I promise not to talk about any rocks or minerals or plate tectonics or anything related. Instead, I will be talking about the environmental consequences of the evolution of oxygenic photosynthesis. So, of course, oxygenic photosynthesis produces oxygen, and oxygen is really important because it's a strict requirement of complex life. Turns out oxygen is also quite toxic, and because life differs vastly in its ability to tolerate oxygen, it's one of the fundamental controls on which organisms will be living in a particular environment. Oxygen is also important indirectly because it profoundly affects the cycling of important elements through the Earth system. So life is impacted by the presence or absence of oxygen far beyond its immediate environment. So for those reasons, the history of oxygen on Earth is a critical component of the history of life on Earth, and possibly elsewhere as well. This is a somewhat schematic representation of the history of atmospheric oxygen on Earth. The details of this curve are certainly the topic of continued debate, but it is widely accepted that both the atmosphere and the ocean were essentially anoxic for the first 2 billion years of Earth history. The timing of this dramatic increase in atmospheric oxygen is also well constrained, and it's typically blamed on the evolution of cyanobacteria. That makes for an attractive story because oxygenic photosynthesis is the only major source of oxygen on Earth. But the story is apparently more complicated than that because biomarkers and isotope proxies point to both oxygenic photosynthesis and aerobic metabolism up to 300 million years before the Great Oxidation event. The most popular way to attempt to reconcile evidence for aerobic metabolism and global anoxia is to invoke oxygen oases, which are locally oxygenated environments within an otherwise anoxic ocean and beneath an anoxic atmosphere. But without anything resembling a modern analog, it's not immediately obvious that this type of environment is even possible. Jim Casting was among the first to attempt to explore the possibility of oxygen oases, and in 1992 he presented this very simple box model in which cyanobacteria are actively pumping out oxygen in the surface ocean, and then that oxygen is free to enter the atmosphere. But upon doing so, it's consumed immediately by reaction with an overwhelming volcanic supply of reduced gases such that the atmosphere remains anoxic. But in this scenario, the surface ocean is not necessarily anoxic because the exchange of gases between the surface ocean and the atmosphere is quite slow compared to biological processes. So dramatic chemical disequilibrium can be established and maintained at steady state. So for reasonable rates of oxygen production, Casting estimated that beneath a strictly anoxic atmosphere, dissolved oxygen concentrations could actually approach 10% modern levels. So that's encouraging for the oxygen oases hypothesis, but this simple model almost certainly overestimates the possible dissolved oxygen concentrations. And that's because oxygen is not chemically inert in the surface ocean, so it's not made and then it passively awaits its opportunity to enter the atmosphere. And even if it were chemically inert, the circulation of the ocean would act to continuously remove it from sites of concentrated production, further reducing the possible concentrations. So 20 years later, I am the first to attempt with a 3D ocean model that these environments can actually exist. So my work is motivated by 3 main questions. First, are these environments even possible? If so, what did they look like? How big were they? And how much oxygen did they contain? And I use a Earth system model of intermediate complexity called GENIE. At its core, it consists of a 3D frictional geostrophic ocean model coupled to a 2D energy and moisture balance model. And in combination, they simulate the physics of the ocean atmosphere system. Then within that framework, GENIE considers a number of biological processes to which I have added probable Archean metabolisms that are not particularly important today, including methanogenesis and anoxigenic phototrophy. Jeannie is probably most famous for its work in predicting Earth system evolution in response to continued CO2 emission scenarios. So I'm actually the first person to apply it to the Archean. In my model, like in the original casting model, oxygen is exclusively supplied by oxygenic photosynthesis in surface ocean cells, and then that oxygen is free to exchange with the atmosphere. But unlike the casting model, oxygen is also subject to both lateral and vertical transport, and oxygen participates in a number of redox transformations during aerobic metabolism. Another minor difference is that my cyanobacteria are nutrient limited, and they must compete with anoxigenic phototrophs for those nutrients. So that's another kind of indirect control on the oxygen mass balance. So taking into account all of these processes and a number of other processes I haven't described, this is the steady state dissolved oxygen map that my model produces. You'll notice that I have used a modern continental configuration. That's because I don't know what the Archean world looked like, and I'm guessing that you don't either. So, dissolved oxygen concentrations range from 0 up to about 6 micromolar in regions of particularly high productivity. And for comparison, the modern ocean has about 250 micromolar dissolved oxygen on average. So these are pretty low dissolved oxygen concentrations. Fish start dying at about 60 micromolar. Nonetheless, this is a pretty exciting result because these dissolved oxygen concentrations are actually 3 orders of magnitude greater than the lowest dissolved oxygen concentrations at which aerobic growth has been documented for microbial life. Okay, so the next slide that I'm going to show you is a cross-section through my hypothetical ocean basin that strongly resembles the Atlantic Ocean. On this figure, the surface ocean is at the top, seafloor at the bottom, and then the poles are on either end. And the point here is that the ocean is overwhelmingly anoxic. Zooming into just the surface ocean, you can see that these environments are truly isolated oases within an otherwise anoxic world. I should note that although I've been referring to them as oases, and it might be tempting to think of them as safe havens for aerobic life and the evolution of multicellular life even, these environments contain poisonous oxygen and ultimately would have been lethal for the vast majority of life on Earth at this time. So a more fitting name might be like oxygen death traps or something similar. Don't know. Okay, geologists love looking at maps and cross-sections, but in case you don't, this is the same data in histogram form. Again, most of the ocean is anoxic, and about 15% of the surface ocean contains micromolar dissolved oxygen. There is, of course, some uncertainty that is inherent to attempting to model the ocean 2.5 billion years ago. So to try to understand how that might affect my results, I have conducted a series of experiments in which I systematically vary key parameters in the model. And this type of dissolved oxygen concentration is reproduced every time over a huge range of conditions. So, although the exact dissolved oxygen concentrations might be sensitive to my model configuration, the existence or possibility of oxygen oases is not. So, in conclusion, oxygen oases are not only physically possible, but I think that they are an expected consequence of oxygenic photosynthesis on an anoxic Earth. Dissolved oxygen concentrations on the order of 1 to 10 micromolar are entirely possible in regions of high productivity. Typically, I see concentrations around 3 to 5 micromolar. Finally, this work is further support for the argument that aerobic ecosystems predate atmospheric oxygen on Earth. And ultimately, what this means is that in the quest for life elsewhere, atmospheric oxygen might not be a particularly reliable biosignature for oxygenic photosynthesis or aerobic life. So, thank you all.
So looking at your maps, you're showing concentrations in an equatorial region and then near the two poles. So in this particular case, if you've actually got a flow model, right, you've got the Antarctic circumpolar current that's naturally going to concentrate it there.
Yep.
So I mean, you've also got, you have equatorial bands that are the main east-west jets, right? So this is all just looks like it's a consequence of fluid processes in the ocean. What happens if you have Pangea?
That's actually a really great question. I am currently attempting to get Pangea simulations up and going. Of course, the Archean didn't look like Pangea either. It's probably as different from the modern configuration. So I don't know yet, but I don't anticipate that the concentrations will be profoundly different. Obviously, the distribution in the map will be somewhat different, but since oxygen is associated with upwelling regions, there's kind of an inherent limit on the fraction of the Earth's surface that can be an oxygen oasis.
Yeah, that's correct. It just, if you get a big continental mass interrupting a global flow, it'll divert things, and you might end up with something completely different.
I mean, it'll divert things and modify the big changes, but ultimately the continents don't drive ocean circulation. That's a function of, heating a rotating sphere. So I would anticipate that the major features of ocean circulation would still be occurring for most types of continent configurations.
Hi, I was just curious if you could go into a little bit more detail on how you modeled the competition between the aerobic phototrophs and the anaerobic phototrophs.
Okay, the anoxygenic phototrophs win the competition for nutrients whenever inorganic chemical reductant is available. So, yeah, oxygenic phototrophs are given a huge disadvantage in that battle.
Since you're a pseudo-geologist right now, I have a pseudo-geochemical question for you.
Okay.
Do you know if the iron banding record supports your idea of these oases or death traps, whatever you'd like to call them?
That's actually a really good question. I don't incorporate sediment burial in my model, and so I cannot explicitly address that question.
Right, but outside of the model, I thought you might have checked the geochemical record to see if it supports the conclusions of your model. That's what I was wondering.
Oh, absolutely. My work is not inconsistent with geochemical proxies, but it's difficult to predict what the signature of these environments would be, and that's because that's going to be a function of both exposure time in the water column, and and these environments are separated from the sediments by several kilometers of anoxic water. So you need really kind of special proxies that can be sensitive to that. And I don't know what those are yet. So.
Any other questions for Stephanie? Okay, great. Thank you, Stephanie.